Now that we've been working in vectors for a couple of days and we know how to work with two-dimensional vectors and we even understand the difference between rectangular and polar vectors, now we're going to try to expand our knowledge out into three-dimensional space. So instead of just dealing with an x and a y axis, which can only take you in two directions, left and right, up and down, we're now going to talk about a third dimension in space, one that travels towards you and away from you. This is what it looks like for a set of three-dimensional axes. You got your x-axis going left and right, as normal. You've got your y-axis going up and down. And we've already learned that going 1 unit in the x direction is called I, and going 1 unit in the y direction is called j. So the tricky part about the third axis, which is eventually going to get called the z-axis, is we have to figure out which way is positive for the z-axis. And to do that, we use something called the right-hand rule. So to figure out the positive direction for the third axis, I want you to point your fingers now you got to use your right hand for this. It's called the right-hand rule for a reason. Point your fingers in the direction using your right hand for positive x, with your palm facing open in the direction of positive y. Then curl your fingers from y towards x, and your thumb will point in the direction of positive z. So if you've been doing that as I've been saying it, you're going to realize that the positive z direction is out of the paper at you. Okay, so positive z is coming at you. And if we travel 1 unit in the z direction, so that vector that goes along this axis, 1 unit, is going to be called k with a little hat. So we now have 3 standard unit vectors. I, which takes us 1 positive unit in the x direction, and if you want to go left, that's negative I. J, which takes you 1 positive unit in the y direction, and if you want to go down, that would be negative j. And k, which takes you 1 unit straight out of the paper towards you, and if you want to go into the paper away from you, that would be negative k. We now are going to take our knowledge of two-dimensional vectors and add on this last piece. So in general, three-dimensional vectors are going to have the form of something times I plus something times j plus something times k. So we've already been dealing with the first 2 parts. Now we're just adding on our third direction. What we need to do next is we need to go back through a lot of the math that we learned for two-dimensional vectors and learn how to adapt it for three-dimensional vectors. So one of the first things that we're going to take a look at is we're going to take a look at how to find the magnitude for the three-dimensional vector. Now the symbol's the same. You're going to see what looks like a double set of absolute value signs around a vector. And we still want to do Pythagorean theorem to find the total length of the vector. But I bet you didn't know there was a three-dimensional Pythagorean theorem. So what you're seeing here, this is how you find the magnitude of a three-dimensional vector. You take the number of units that you're moving in the x direction, square it, the number of units that you're moving in the y direction, square it, and the number of units that you're moving in that new direction, the z direction, and square it, add all 3 of these squared numbers together and take the square root of it. That's actually the three-dimensional Pythagorean theorem. So let's work on an example. If somebody asked you to find the magnitude of vector v, first of all, the symbol for that would look like this. So you're going to have vector v inside of what looks like a double set of absolute value signs. And so what we're going to do is we're going to take -6, that is our x component, and square it. We're going to take the 7, which is the y component, and square it. And now we're going to take that the z direction component, which was just 1, and square it. So all 3 of the numbers that come in front of I, j, and k are going to get squared, added together, and then you got to take the square root of the whole thing. So this is going to make 36. This is going to make 49. And this is obviously 1. So we have basically 50 plus 36, which is going to be the square root of 86. Now, your next thing to do would be to try to simplify this radical if you can, but if you can't find any perfect squares that divide evenly into it, then you can leave it alone. 86 doesn't have any perfect squares that divide evenly into it, so you can leave this alone. The next thing we want to do is we want to go back through some of the arithmetic that we learned how to do with vectors, like addition, subtraction, and scalar multiplication, and learn how to adapt those to three-dimensional vectors. So when we did two-dimensional vectors and we were doing adding and subtracting, we learned that you could only add like components together. The i's had to go with the i's and the j's had to go with the j's. Well, the same thing is true for three-dimensional vectors. Now, you just have to remember that you can only add even the k's with the k's. And for scalar multiplication with two-dimensional vectors, we learned that the constant that was out in front had to distribute to both of the components, the i's and the j's. Well, now that you have three-dimensional vectors, you also have to remember to distribute them to however many k's you have as well. So let's practice with a few examples. Here I have two three-dimensional vectors. U is going to be 5i minus 2j plus 4k, and vector v is going to be negative 6i plus 7j plus 1k. And the first thing I'm going to do here is I'm going to try to add them together. So remember, i's go with i's, and when I add up the i's between these two vectors, we're going to have negative 1i. And then I'm going to add up the j's. So negative 2 plus 7 makes a total of 5j's. And this is what we had done in the past with two-dimensional vectors, but now here comes the third part. We also have to add the k's. K's go with k's, so a total of 5k's. And that's the sum of these two vectors. Just be careful, as always, with subtraction. Remember that when you're doing the subtraction, you have to distribute the negative onto each and every part of vector v. So you can remind yourself by saying 5 minus 6i. So that's going to be positive 11i. Here we're going to have negative 2 minus 7 more j's, which is going to be negative 9j. And last but not least, 4k minus 1k is going to be 3k. So that's adding and subtracting of three-dimensional vectors. And now we're going to do this, which is a scalar product. In the past, when we had seen a number in front of the vector, we just distribute it to all of its components. And here there's nothing new. You're going to have to multiply the 3 onto however many i's you have, and you're going to have to multiply the 3 onto however many j's you have. Now that we have our third component, we're also going to multiply it onto however many k's we have. So this would give us a total of 15 i's and minus 6j's and plus 12k. So whatever you're doing, just make sure you understand now it's extended out to 3 directions. So besides doing basic adding, subtracting, and scalar multiplication, vectors actually have 3 other kinds of multiplication that you can do with them. Besides scalar multiplication, we have dot product, we have cross product, and we have something called triple scalar product. So today I want to teach you about one of those other kinds of multiplications with three-dimensional vectors. It's called dot product. And actually you're going to use dot product a lot in physics, although in your current brand of physics, if you're not talking about vectors, they won't necessarily show you this, but you will definitely use this in college level physics if you need to take one of those courses. In dot product between two vectors, what you end up doing is you multiply the coefficients from the front of only like components, and then you add all 3 of those products together. So you take the coefficients from in front of the i's between the two vectors and multiply them together. You take the coefficients in front of the j's, you multiply them together, and you take the coefficients from in front of the k's from both vectors and you multiply them together, and then you add those 3 products together. So if you're given vector u is a in the I direction, b in the j direction, c in the k direction, and vector v is going to be d in the I direction, e in the j direction, f in the k direction, you're taking the numbers from in front of like components. So the a and the d both come in front of the I, you multiply them together. You take the b and the e because they both come in front of j's and you multiply them together. And you take the c and multiply it with the f because they both come from in front of the k's. So your answer for the dot product between vector u and v would be a times d, b times e, c times f, and then you would add those 3 products together. One of the things that I want you to notice that's very special about a dot product is the result of a dot product is actually just going to be a scalar. Because when you do this, you don't put the i's or the j's or the k's back on your answer. It's just the numbers that come from in front. Now, in physics, if you are taking physics, I'm sure that you've seen this formula. Work equals force times displacement. But we know that force is actually a vector because it has to have direction. And displacement is actually a vector, but work is not a vector. Work is a scalar. This formula, work equals force times displacement, only works when the force and the displacement are aligned. In other words, they have to be going in the same direction. This technically is actually a dot product between two vectors. Now, if you're not doing vectors in the physics class, your physics teacher is probably not telling you this yet. When you go to a college level class, you will definitely see the work formula expressed in this form. So let's practice with a few actual vectors down here. If vector u is 5i minus 2j plus 4k, and vector v is negative 6i plus 7j plus 1k, let's find the dot product between vector u and v. So first we start by multiplying the numbers in front of the i's. That's going to give us negative 30. Don't put an I on this, it's just a number. Then we're going to multiply the numbers from in front of the j's together. That's going to give us negative 14. And then we're going to multiply the numbers from in front of the k's together, and that's going to give us 4. When you put all of this together, negative 30 minus 14 plus 4, that should give us a total of negative 40. Now, one thing that I want to point out to you about this particular kind of product is we're going to test its commutativity. In other words, let's see what happens if we put the vectors in a reverse order. What's interesting about this kind of multiplication is when you put the vectors in a reverse order, that means you're taking the number from in front of v first, and in front of v's I component first, and the number from in front of u's I component second, you're still getting negative 6 times 5, which is still negative 30. And if we put the 7 first and the negative 2 second for the j's and multiply them together, you still get negative 14. And if you put the 1 first and the 4 second and multiply them together, you still get 4. So your dot product turns out to be negative 40 anyways. So what this proves to you, hopefully, and you could imagine doing this with other vectors as well, is that the order for dot product doesn't matter because you're still going to end up multiplying the same two numbers in front of I in either order, the same two numbers from in front of j in either order, and the same two numbers from in front of k, so it won't make a difference who comes first and who comes second. So the last thing I want you to write down about dot product is the fact that it is commutative. That's kind of important to know. So dot product is a commutative operation. It doesn't care who goes first or second. You'll still get the same answer in either order. Okay, you are now ready to try homework number 138, which is a worksheet.